All right, let's go. So tonight we are going to be talking about, it's just me. Unfortunately, my guest couldn't come, but that just happens sometimes. We're going to have another guest next week and the following week and the following week. So hopefully you're going to be able to put up with me tonight. But next week is for sure is a must-see TV. Jim McTaggart-Cowan's going to be here. It's going to be awesome. Real stuff. So tonight I was going to take the opportunity to talk about some stuff that I've been working on for a while that leads into what I'm currently doing, but it also relates to some aspects of the course for those that are in the course, and then just in general, how you do biospheric analysis or Earth system type of analysis. So I've prepared some slides and I will share them right now. Just a sec. Just a sec. Share this. Share. Okay. So can you see my screen right now? Just let me know. Chats. Yes, you can see the screen, right? Awesome. Okie dokie. So I want to talk about integrated biospheric analysis of Amazonia. So this is kind of related to things that we're doing in the course. For those in the course, how do you take a situation similar to like the Alaska fishery or any given kind of regional, various different scales, like whether it's a local to a regional or even to like a macro level problem, and then do integrated analysis. Like, what does that mean? What's the process for doing that? Okay, and I'm going to particularly talk tonight about analysis of Amazonia. So why do we do this kind of analysis, and what's the moral imperative? So for one, a concern about the planet and the future generations. That's one moral imperative for doing this kind of work. You also see in the media and political coverage various different types of stories. So I'm referring to anything related to climate change right now has various different slants on it. Often we'll get really kind of apocalyptic stuff, and then we'll get on the other end of the spectrum, we're going to get really watered down and fake news in terms of negating the science. So it can be confusing, right? Like confusing as to what is truth or what is something that we can kind of believe in. So, and one other reason for doing this is just being curious. In this case, learning about Amazonia and system dynamics and so forth, and how you might approach this. So the motivations for this type of approach or doing this are multifaceted. And in fact, what I'm going to show you now, this work, was motivated purely by the third one. Curious, interest in system dynamics, not much about climate change, to be honest, at that point. I mean, it was an issue, but it wasn't, actually, no, that's not true. Part of it was motivated by some papers that came out around climate change, and I'll get to that. So who the heck am I and why would you listen to me about this stuff? That's the question you need to ask in any given situation is who's presenting it and why, what's their story? Like why listen to them? So my background is in environmental science and design. This particular work is from a master's thesis that I did back in 2008. That was published in a chapter in a book. And then the model that I established that I'm going to show you, it's interesting because at the time it was like when you ever do these projects, often you wonder, oh, well, is this for real? Like, is this actually legit, or is this going to have some longevity and so forth? And that was, now it's a while ago, right? And with modeling, you never, I don't know, it can be tricky because you come up with a model and then you think it's representative of the world, but then it may or may not be representative of the world. So you kind of have to see how well your model predicts things, what kind of predictive power it has. So in this case, this model that I developed that I'll show you, which is more of a heuristic model, was put to the test then between 2000 and 2005 using data to see if it actually made sense. But then also it's been put to the test over time, because now, given that, you know, it's been since 2005, it's been more than 15 years since this work was done, to see if any of the patterns that were picked up in this integrated biospheric analysis, you know, reoccurred. Like, was this just an anomaly, or is this something that is something we should really be worried about? And you can only see that over time. And what we are seeing today, or what we have seen in the last couple of years, this was in 2019, is the specific event that I'm referring to, which is the summer in which, in 2019, I guess it was probably June and July and August of 2019, where there were a lot of fires in the Amazon. Do you remember that? Does everybody remember in 2019 where they said the Amazon's going to burn down? Does anybody remember that? It's a couple of years now. Yes, right? It was a big deal at the time. So I'm going to go through that, and I'll show you why that well, not why that happens particularly, but some analysis that supports what was going on and what were the things that were driving it in that direction. Okay, first, Amazonia. So the context. So we're talking about, so when we talk about the Amazon, has anybody been to the Amazon before, or any parts of the Amazon? Maybe people from South America, if there's anybody on the line from South America. The Amazon is not just, it's a big, big, big area. So you have the Amazonian rainforest, which covers multiple different countries, ranging from Peru, Bolivia. In Peru, you've been to Peruvian Amazon, right? So there's the Peruvian Amazon, there's the Bolivian Amazon, you have parts of Colombia, you have a large part of it is in Brazil. So you kind of have to specify what you mean by the Amazon when you're talking about the Amazon. It's a very big area. I'll show you a map of it. So the problem here is to need to assess the spatial patterns and ecological processes in response to disturbances, and you will see what kind of disturbances we're talking about. And then also understand that in this context, the Amazon and tropical systems, but particularly the Amazonia, play a very critical part in the Earth system. When I say the Earth system, I mean the global Earth system, atmospherically, hydrologically, and biospherically. Okay, and so in that context, tropical ecosystems are a critical part of the Earth system from an atmospheric standpoint, as a buffer for energy, water, and carbon dioxide. There's a lot of CO2 that comes in and out of the Amazon, that's stored in the Amazon, that also fluctuates in and out. There's a lot of energy and water that comes in and out of the Amazon as well. So all of those constituents are very important to atmospheric function and global atmospheric processes. So therefore, when you're looking at the Earth system, you see this kind of big chunk of green stuff as a critical component to how our current Earth system works, atmospheric processes. And if there's major disturbances to the Amazon, there may be major impacts on global atmospheric processes. So currently it's a hot topic. Why? Reported high number of fires. The smoke that was going into Sao Paulo and the global media coverage has exploded. This is in reference to the recent fires. You haven't heard much about it yet, right? This past year, but you know, just wait until you'll see in the data. We're in May now, wait till June, July. We might see that pop up again. So this is the region, and this map here you can see, it's a little low resolution, but this gives you a rough idea of the area. So this yellow, you can see the yellow border. There's the green vegetation in this yellow border. So that is the border of the Brazilian, what's called the Brazilian legal Amazon. So that's the Brazilian part of Amazonia. all of Amazonia that falls within Brazilian boundaries. So you can also see that there's Amazonas, you can see Acre, you can see Mato Grosso, you can see Pará, and all of these different states fall within, those ones in total fall within the area of the Brazilian legal Amazon. So that is and actually that's the definition of Amazonia that I used for this project, because that's the part of the, in fact, even a subset of that I used for this project. So it's roughly about 5.8 million kilometers squared. So it's a big area, you know, like it's not a small little rainforest. There's a lot of it. And, you know, like South America, for those of us in North America, we often kind of, I think we think of, you know, we have a spatial distortion with other parts of the country. Like if you look at sheer landmass, South America versus North America, I mean, there is a lot of landmass in South America, okay? So, and the Amazon is a big chunk of that. Very rich in biodiversity. It's a humid tropical rainforest that is coupled with the atmosphere. So does anybody know what that means? Coupling, what coupled with the atmosphere? What do you think that means? When you say something's coupled. Like linked, right? Dependent upon. Exactly, John. Linked. In fact, added, interdependent, absolutely. So it is so coupled, and the common person doesn't really know how coupled it is. It is so linked and so interdependent and so coupled that it's estimated that roughly about 50% of the incoming precipitation, so the 50% of the rain that falls in this rainforest, is actually coming from the forest itself. You see what I'm saying? So that's moisture that has been evapotranspirated from the forest through photosynthesis into the atmosphere, and then condenses and then gets cycled back into the rainforest as precipitation. So that cycle is called atmosphere-biosphere coupling. So it's like this self-sustaining system, okay? In addition to that, lungs of the planet, exactly. So this is, and I'm gonna show you some images of actually how that works that I took while I was there, that shows that on a day-to-day basis, how that actually works. It's essentially like a big lung or pumps, right? It is constantly circulating CO2 and water vapor and so forth, and energy is driving that process between the boundary layer. So that's the thin layer of atmosphere above the earth and the rainforest. And there's major land use challenges there. So there's some big issues, as you can see, and this is an old article, like from way back. This would be much worse now. This kind of purple area is land use change, so deforestation. You can see it happens all along the bottom there. And that's known as the arc of deforestation. So this arc where there's been a lot of development and continues to be development, even if the modern map would be just like this, but even more intense. And so what do you think's driving that purpleness there? What has driven that? Is it just people chopping down trees for the hell of it? Profit, cattle, exactly. Cattle, what else? Agriculture, absolutely, Linda. So it's development, you know, it's agriculture, people wanting to make a living, small scale. In some cases, it's smaller scale, pastoralists. Cattle is often that, like you have a smaller group, but then you also have large scale cattle ranching, and then also large scale agriculture. So particularly in this state, Mato Grosso here, it's quite famous for that. It's quite famous for large scale agriculture. And therefore it's known as being a hotspot for land degradation. So social and economic forces, deforestation is a dominant force in affecting the ecosystems. The arc of deforestation around Mato Grosso has intense activity. Some studies, even going back, suggested that up to 40% loss of the forest by 2050 based on agricultural expansion alone. So you can see there that even in those modeling studies, that the press for economic development, agricultural development is directly linked to degradation of these ecosystems, this part of the biosphere. And you can actually see it very much more clearly when you link it with market signals. So particularly in the past, there's been some good studies on soy. So there's certain crops that become, quite valuable or quite high in demand. And then there's a push for cultivating them, either through just purely based on the demand for them, or if perhaps there's a trade deal that's struck, or a subsidy, whatever it is. But soy was one of those ones at one point in time. And you could see that the spike in soy consumption and demand, which largely came from China, led directly to, was closely correlated to land use change in Amazonia. So, given the context, we've got this piece of the biosphere, and that's what we're trying to think about, is how do you make sense of this world that we're living in, where we're in a climate emergency and everything's going to heck. So that can be much, well, that's it. This is an interesting point that you're going to bring, and we'll get to this. So how do we look at this stuff? Like, how do we do biospheric analysis? So how do we even look at an ecosystem, right? And this into itself, there's, walk out to UBC or walk over to McGill or SFU or UVic or wherever, any university where you got like a forestry or biology department, and you're going to get, or geography, and you can probably get in a week-long argument with 10 different people about what an ecosystem is, or how should we be looking at ecosystems. So is it a bunch of different species inhabiting a region? Like, is that what we need to look at in order to understand this part of the biosphere? Is it just a bunch of processes like water and nutrient cycling around through plants and soil? So, I mean, it's a lot of different things. And so for those of you who have a background in forestry or ecology or biology, you'll know that, if you take a course or do some study in population ecology, the methods, the science, even the paradigm is a lot different than if you were a hydrologist working in an ecosystem in a forest, or looking at, say, forest productivity or carbon sequestration or whatever. So there's these different paradigms, if you will, or different ways of looking at it. And so ecosystem ecologists tend to look at how the biotic and abiotic components systematically interact. So my background is more in ecosystem ecology. I identify as that, not a population ecologist. And that's just the way you look at it. We say, well, what's going on with the nutrient cycling, and what's going on with the hydrological profile, and how are the carbon sequestration? What are the dynamics of the system, right? Nutrient dynamics and so forth. Whereas landscape ecologists tend to look at spatial distributions over landscapes. That's another kind of way of looking at things. There's some subtle differences between landscape ecology and ecosystem ecology, but there are differences. And then population ecologist or community ecologist will look at an ecosystem in a much different way. They might be more species-centric in their approach. So you kind of have to choose the paradigm that makes the most sense depending on the problem you're dealing with. So my perspective lands usually, in most of the time, lands in the ecosystem / landscape ecology camp. And this is because the questions that I am usually most interested in pertain to the factors that an ecosystem ecologist would ask, those kind of questions. Looking about the impact of climate change, the impact of drought, the impact on different type of land cover changes and so forth, even fragmentation of landscapes. So for example, are there disturbance factors that would affect key support systems that could cause a significant shift, right? That would be one of the questions. In fact, that is the question that I was trying to get at with this Amazonian problem, is, are there disturbance factors? Are there disturbances that would affect key support systems, like fundamental aspects of this system, that could potentially cause a shift, right, of the system? So this sounds familiar to some of you, I think, right? Like, what is the word that I'm kind of getting at with that question? Starts with R. There we go. Mirel for the win. Resilience, that's what that question is really getting at. Saying, how resilient is this ecosystem? And are there disturbance factors that can push it beyond certain thresholds that cause it to shift? And that was, and In addition to ecosystem ecology literature, one needs to consider the unique features of the system. So in this case here, that's why context is really important. So one being that there are diverse disturbance factors that work cumulatively. So in the case of the Amazon, already we've talked about deforestation as a result of agriculture and pasture creation for cattle and so forth and so on, and just settlements. We have fires as well. So fires are a big factor in Amazonia, and as we'll get to that. We have road building. So road building is closely tied to the development aspect. We have droughts. These are some of the major things. So drought is just purely a reduction in precipitation coming into the system, right? So this system, in addition, another characteristic of this system, as we've discussed already, is that it's highly coupled with the atmosphere in what is called as negative feedback system, right? So negative feedback systems are those that keep a system in stability, right? So what would be an example of a negative feedback system? Like in the human body, what's a classic one? When you go out running in the hot weather, what happens? Perspiration, lose water, exactly. And that's a means of, or heat stroke can happen too if you go beyond the threshold. But the whole idea is there you have this intrinsic homeostatic mechanism built into your body, how it functions to perspire, to help control the heating and cooling yourself off by having that energy, having their sweat evaporate, right? Takes heat away. So you have to understand that these, in this case, we have a similar type of system. We have a negative feedback system, right? The trees are giving, this rainforest is fed by the trees themselves. It sustains itself, right? This system is highly coupled with this negative feedback system, and it sustains this rainforest as a rainforest, right? So another type of negative feedback system is the reflection of shortwave radiation from high albedo. So in the Arctic, snow. So snow stays cold, like you manage the energy because of the fact that you have a large proportion of the energy coming into an Arctic system is reflected back because of the high albedo. Now that becomes a problem when it starts to melt. As you'll notice in the winter, and say out east, when it starts to kind of warm up a bit, and you start to see on the road, the pavement starts to show. So what happens as soon as the pavement starts? You start to see pavement in the period of time where the temperature's going up and the snow is starting to melt, right? As soon as you start to see the pavement, boom, the rate goes up, accelerated melt, exactly. And that's a positive feedback system, right? It's pushing it into another state. And the reason being is you're not having that energy reflected, rather you're having the energy absorbed, right? It's absorbed, and then that contributes to the warming, which accelerates the melting. And this is the concern is with climate change and the melting of ice caps and so forth. What is changing is the albedo of the surface of the earth. So there's this negative and positive feedback systems. Negative, sustaining, positive, pushing to an alternative stable state or to an unstable point at which things shift. So where did this all start with? I want to go through how I got to this kind of data and the conclusions. And I am a big fan of actually going to the places. As you'll see, I actually didn't need to go to the Amazon to do this work. I could have sat in an office wherever in the world and just downloaded data and done the processing. But I wanted to go there and get to the bottom. At the time, I didn't know that. So start of the voyage from Montreal, so that's where I was based, to Brazil and getting situated. So I flew down to Rio de Janeiro, met my father. Then I went to Salvador da Bahia. I did a month of Portuguese just to, get functional. I had spoken Spanish before, so it helped. And it's always useful when you're doing this kind of field work to have some degree of capability in the local language. And it was surprising because in Brazil, I'm glad I did that, because although many of the scientists spoke English, not many of the locals spoke English, especially in the Amazon. So I went to Salvador, did that about a month, got up to speed, went back to Sao Paulo, then went to São José dos Campos, which is just outside of Sao Paulo, to work at the space agency. So Brazil has a space agency. It's called INPE, Brazilian Space Agency, Instituto Nacional de Pesquisa Ambiental. I forget the last part of that. But it's focused, like they don't do as much stuff with, say, sending spaceships up and stuff like that, at least at that time. That was, you know, a few years ago now. But they do a lot of stuff with Earth observation. Portuñol, Español en Portugués. And they do a ton of work with Earth observation. They have very advanced remote sensing. So with a good handle on the language, it was helpful to go there and just hang out with the people there who were working on, you know, with their land cover change, their mapping. So just to get a handle on what they're doing, what kind of tools they're using, etc. It's always good. So to the field at that point in time, with a good handle on the data and the satellites and all that kind of stuff, I went to the field to see the land, right? So you can see on the right there, we have Salvador in the top right. We have Rio de Janeiro and Sao Paulo. So I went, now, I mean, this isn't common. A lot of people, when I talked to my friends who had met in Sao Paulo, said I was going to take the bus to the Amazon. They said, "Are you crazy? Like, nobody, everybody would fly there. It's a bit of a haul. That's a long way. It'd be like taking the bus essentially across Canada." The reason why I chose to do that was to see the landscape. I'm dealing with a large scale problem, so I wanted literally to see the land and the transitions. So I took a bus. It took about 3 to 4 days from Sao Paulo, nonstop, up through along this, not directly along this line, but roughly up to a place called Porto Velho. And it was interesting because I was able to see how all the bottom part there is quite arid and deforested in many places. I literally saw those places that had been deforested and where the fires were burning and where the cattle was and the different crops and so forth, up to Porto Velho, which is kind of the, at least at that time, was the northernmost point where you could go to before you could travel. You could no longer travel by road. You had to travel by boat from there. I wish I had some photos of this boat ride because it was something else. So I went down the river in Amazonia, and this is a trip. So I found a large boat that transports cargo and people along this river. So it's called the Rio Madeiras. It's hard to see in this, but you can see it's very light. But there's a river that goes from the south to northeast. It runs to the northeast, and it goes from that red point all the way up to the bridge. So the connection of those rivers, which is the Amazon, where the Rio Negro and the Rio Madeiras meet. And that is, the meeting of the waters is something unique too. It's kind of interesting. So I rode in this boat, and again, I got a chance to this is where the commoners would travel. These are like your farmers and your middle class or average, not even Brazilians would travel on this boat. It's really inexpensive to get around anywhere around Amazonia. And they're big wooden boats. Supply about 100 plus people on this boat. And so I took that. At first, it was quite mellow. I thought it would be kind of a nice, spacious ride. The morning I got there and got on the boat, and there was no hammock strung up. I went to get a coffee. I came back, and then I couldn't even find my hammock when I got back. There was like 3 hammocks strung on top of it. But, you know, it was a good 5-day trip. Like, it took a while with that big old boat, but it was fun. I got to get to know people, got to understand a little more about what makes people tick there. The music, dancing friends, and even an Amazonian cowboy became my buddy on this trip. So what did I see? Now, this is important. This is important for us in the course about observations, like the Leo network. And this is what we can get from observing things. It's important to observe and make note. One of the observations, and probably the most important one, was at every day along this trip, and this is what it looked like in this photo, right? So this is the river, and this isn't the Amazon. This is a feeder to the Amazon, and it's still quite a big river. When you get to the Amazon is a big river. It's like a moving lake, right? So I made a point of getting up early every day just to see what was going on, because one of the things I was concerned about was this you know, the dynamics of this system, right? So I observed what was going along the river and at the interface of the forest and the atmosphere. So you can see this photo here, which is dated 7:10 a.m. on July 8th, 2006. It's when that first photo was taken, right? Very clear, not much going on there. The next photo on the left-hand side is taken at 1 p.m. Actually, it's the same day at 1 p.m. So you can see what's starting up there. It's becoming a little less clear, right? You can see things are starting to happen. And then at 6 p.m., same river, just a little further down river by this time, at about 6 p.m., and there we go. You can see on the right-hand side there what's happening, which is it's a cumulonimbus cloud. So what does that tell you right there? What's that showing you? In one day, that's across from morning up until the afternoon. There's a lot of stuff going on. There's a lot of photosynthesis going on. There's a lot of exchange. Unstable atmosphere every day though, like this is what happens pretty much every day, a lot of moisture in the air. So that moisture there, that moisture is coming from the forest. I mean, this is the 50% of the rain that comes into the Amazon it's largely that, which is evapotranspiration. It's water vapor that has been evapotranspirated from the forest into the lower level of the atmosphere. And sure enough, what happens later as it starts to cool off, we get torrential downpours of rain, and I've been caught in them before. Okay, so concepts, context, great. Concepts now though. Resilience. So in this case, we've got to look at this, or at least have to, but the goal was to look at, well, how does this whole idea of resilience fit with this biospheric problem, right? So we know that Holling's definition from 73 is the ability of these systems to absorb changes of state variables, driving variables, and parameters. And we have on the right-hand side there an example from Beisner's paper in which we show a stability landscape and then a shift in variables that results in a state shift. And we also see a shift in parameters, which can also cause a state shift. So it may be dictated by certain conditions, the amount of biomass, temperature, precipitation, nutrient availability. This is from Martin Scheffer. And then also landscape pattern may be a representation of states in ecosystems. So there's this relationship between kind of what the patterns in the landscapes are and then what the resilience of those landscapes might be as well. And that's from Van de Kuppel and Rijkerk classic paper. So, well, how do we put this into some sort of sensical model given this situation? Well, the idea here and the problem is, in fact, what motivated me to look at this in the level of detail over 3 years, which is essentially how long it took, was a paper I had read in 2004 by Peter Cox and his team, Cox et al., which is a British atmospheric scientist, on the Amazon dieback in response to climate change. He wrote a paper with his colleagues about models that they run based and with the business as usual scenario of greenhouse gas emissions. They predicted that there would be a large scale dieback of the Amazon over between 50 to 100 years as a result of the atmospheric changes that would occur. Right. And I thought to myself, oh my God, the Amazon's going to die according to what these folks are doing. I got to get a better handle on how resilient they are. Like, how do you then actually look at this? So part of it was like studying the context, but part of it was looking at resilience theory and then trying to establish something that made sense. So in this case, this was my attempt at this, which is to look at what are the two states that we're primarily concerned with here. And we talked about this in our assignment. What are the states? A fishery that's healthy and a fishery that's like degraded and not functioning. I mean, those would be two states in that context in Alaska or Eastern Canada. In this case, we have a vibrant rainforest, healthy, lots of evapotranspiration and precipitation, everything's going well. And then we have a savanna where you have different characteristics. So those are the two major states. And these are the states that are argued by Peter Cox et al. That there would be a state shift from rainforest to savanna as a result of atmospheric forcing. according to their model. So I looked at this and said, okay, well, what are the things that are at work? It's it's not just the atmosphere that's working on this, it's the intrinsic the functioning of the coupling process, and then also some on the ground processes like fire, excuse me, sorry, fire, land use change, and the fueling of fire. So land use and deforestation is one thing that's contributing to the degradation of forests. The fueling of the fire through fires that are set, and then also the sustaining processes, so the negative feedback system, which is a high precipitation and evapotranspiration negative feedback loop, and we have a positive feedback loop at the bottom with the fire, okay? I've also included climate forcing, called it climate drying, because that's what was happening, but it's climate forcing in both circumstances, because that's one of the things that's a concern in the situation, okay? So this is my attempt at a model, right? A resilience model, a state model, to say, look, these are the two states, these are some of the variables that are at work, and if some of these get pushed beyond a certain threshold, we can see this state transition happen. Okay, so I've explained this already, negative feedback system. The red arrows are positive feedback systems. This indicates a movement towards instability. So positive feedback systems like the melting of snow moves something towards instability, like can promote a state shift. Fire will promote a state shift. Why? As things dry, fires start. More fire leads to less evapotranspiration, leads to more smoke in the boundary layer, and smoke inhibits rainfall as well. So there's this positive feedback loop that's well documented in the literature by Cochrane and various other experts on forest fires in the Amazonia. So more fires, less rain, more drying, more fire. See, it's like that accelerated melting snow idea, which is a problem because as that gets out of control, that can lead to accelerated state change. So analysis, we've got our model. And we've got to test it then. This is one thing. It's nice to come up with a model, but how do you actually measure this stuff? So part of it was looking at the time frame for this. And we've always got to think about this. We can think about resilience of something in paleo terms, like in long time frames, or we can think about it in shorter time frames. And in terms of human impact on ecosystems or in the environment, a lot of the development that has occurred, impacts have occurred in the last 50 to 100 years. So therefore, this is the timeline. We have a pre-industrial timeline looking at 1491 as contact, but then also citing that before contact, there was still large-scale agricultural production as evidenced by something called terra preta, which is large mounds of black earth. So the Amazon was not an undisturbed massive forest before contact. There had been land use change of various sorts. There had been use of resources, but that was certainly accelerated as more of a population came in, and certainly a more development-focused population. So past 1491, we started to see small-scale disturbance by sugarcane and cacao plantations. And in 1870, we had the start of the rubber boom. So the rubber boom was a big deal in terms of expansion and population expansion in Manaus particularly. It fueled a lot of the development of the city. For those that have been there, there's an opera house in Manaus where they actually literally have operas in the middle of the rainforest, which was financed through the development of the rubber boom, the money that was made from that resource. So in the 1950s, we started to see the start of the agricultural development in southern Brazil. So that arc of deforestation started around the 1950s, initiation of a militaristic development policy. So for those that are familiar with Brazil, they have these kind of, certain times in history, some more, some less, these militaristic or very kind of top-down planning processes. Avança Brazil, advance Brazil, Brazil em ação, like Brazil in action. So we're going to move and open the frontier. We have it in North America too, but it's more pronounced when you're dealing with the Amazon, I find. And so this kind of push towards expansion into the rainforest actually led to the creation of roads. So 1967, we had This, I think, I don't know if it was completed, but was started at least, the BR-167 Trans-Amazonia Highway. And whenever you build a road, that just opens things up. Like that just opens access, which of course was going to lead to more impacts. And it has. You can see that in the literature around roads and deforestation. So forward to 1995, we had implemented policies to support ethanol and soy production, as I mentioned before. So in the 90s, we started to see a push for ethanol, so bioethanol. And if you're in Brazil, you can see a lot of the gas stations have ethanol-based fuel, right? And I think that was driven largely for energy independence. And so we had these large-scale impacts. Soy started, as well as ethanol. This is fuel for deforestation. But then in the late 1990s, so 1998, 99, and then again in 2005, we saw some very significant droughts. Now, there may have been some before. I'm not as aware of the extent of the droughts before, but in the literature for sure, in 98, 99, 2005, and then also in 2019, we had these very, very big droughts, which impacted, and I'm going to show you them. So the period of study then, to put this in context, then how do you actually take that model and measure it or put data to it, was from 2001 to 2006. That's the period of study to test this resilience model with some data. And that was largely because I was using satellite data, and that it was only launched in 2000. That's when the satellites I used went up, and they've been up ever since. Okay. So this is some data. Now this is getting at the state change. How do you measure a state change in this case? A state change is whether there's a forest or not a forest there, right? So how do you know across a large scale area like the Amazon or a component of it, how much land is in what state or what another state? So I use something called MODIS EVI, Enhanced Vegetation Index. So it's a satellite product. So this is coming from two satellites. In fact, there's a satellite called Aqua and Terra that are in asynchronous orbits. So that each of them are, they cover the one point on the Earth each once a day. So you get 2 shots per day with this sensor, each coming from a different satellite, but it's the same sensor, like it's the same type of sensor. So you can get a morning shot or an afternoon shot anywhere in the world at 1 kilometer spatial resolution. And this EVI, Enhanced Vegetation Index, is basically a measure of the amount of photosynthesis that is going on the Earth. It's detecting the reflection of sunlight hitting the Earth and coming back to the atmosphere. But certain parts of the electromagnetic spectrum, it's actually the red and near infrared, that then when you do an index on them with the blue, in this case for EVI, gives you an idea of how much radiation is being absorbed and reflected by vegetation, which is a proxy for how much photosynthesis is happening. So it's an amazingly powerful thing, because you can, using EVI, or another one you may have heard of as NDVI, Normalized Difference Vegetation Index, that is a proxy for what is going on the Earth biophysically, like how much photosynthesis is happening, which of course tells you a bunch of other stuff, like potentially how much carbon is being sequestered and so forth. So I use this data because I could get 2 shots a day, every day, 365 days a year. So that's a lot of data, and it's across the whole Amazon in morning and afternoon. 1 kilometer spatial resolution, which is pretty decent for something of this big size. Like if you're doing a smaller study, you might need finer spatial resolution, but this is a satellite. So, and I made 16 and 30-day composites, meaning that I took images from 16 days and then added them up, and then took the maximum value. So the reason why I've used these composite images is because there's a lot of clouds in the Amazon. So you're not guaranteed a clear shot at any point in the Amazon at any given point of day. So in the rainy season particularly, it's often covered by clouds, and I can't see the sun reflecting off of the Earth to the satellite. So by using a composite image, which is basically taking the best shot at that one point over a 16 or 30-day period, I can almost guarantee that I'm going to get at least 1 clear shot over, say, 30 days. So this product is particularly good. It's free. This data is free. You could get it and use it if you wanted to. It's high spec, relatively high. They call it medium. MODIS stands for moderate resolution, but it's pretty good for global studies, 1 kilometer, or even 500 meters in some cases. But the spectral resolution is very good. So you get 36 different bands, or 36 parts of the electromagnetic spectrum are reflecting back and detected. That allows you to look at a bunch of different things, right? And then the temporal resolution is quite high. So this allows, by using this approach, this allows us to look at seasonal variation. We look at the change over months or days, but in my case, every 16 days and 30 days, we can look at the change over that one period over a season. And it also allows us to look over the years, how it changes between years, and then some longer term trends. So that's the beauty and power of using remote sensing in this case. So I did a transect study here. So this is the state called Mato Grosso, which I mentioned, which is in the southern part, which is the most degraded. I ended up focusing on this state, but I wanted to look at, okay, when you're doing an ecological study out in the bush, you often will do a transect to try and get some sort of behavior over space. So I wanted to do the same thing here. So I decided to make 10 by 10 meter or kilometer transects. I think those are 10 by 10. I forget what the actual length is. Could be a 100 by 100. Actually, if I look at this, those are 100 by 100 if you look at the scale. So these are 100 by 100 squares that I then took the average value of key parameters across that and made a transect study. Think of this as this would be looking at all of British Columbia, that kind of thing. So looking at mesoscale trends. So I did 1, 2, 3, 4 across the vertical and then 1 horizontally. Okay. And the scale on the right tells you 0 to 10 means bare earth, and then up to 100 means it's completely green and in fact oversaturated. So super, super vegetated. Okay. So that's vegetation. That's going to tell us the state. Is it a rainforest, or is it a savanna, or is it in some sort of transition zone? The other part of it is to look at what are the things that contribute to this. And we know that water is really important here. So in this case, I chose to use something called TRIM, and TRIM is called Tropical Rainfall Measuring Mission, which is, again, it's a satellite product, but it's a radar. It's a precipitation radar, which is different. It's not detecting reflected radiation from the Earth. Rather, it's sending out a signal and then getting that signal back. So it's much better for things like precipitation, and you can use radar for, it's like a depth sounder almost to some degree. Sonar is a type of sound-based radar. Whereas if you wanted to look at topography of stuff, radar is really good, and precipitation is actually pretty well measured using radar. So I use this, which is a global product that has quite coarse resolution, like spatially. It's a 2.5 meter degrees, sorry, which is it's pretty coarse in terms of what each pixel is. But that's all I needed. I needed a coarse take. So you can see here, this is March of 2005, and we had monthly shots for each of the months across that study period, January through December each year from 2000 to 2006. So that is March 2005, which would have, you can see that it's pretty high. It's pretty blue across the board. Okay. This is July of 2005. Okay. So what is the difference between March and July, particularly in Mato Grosso? What does it look like there? Super dry, absolutely. Okay. No rain. So I'm going to show you, just one sec. I'm going to show you a video. Okay, watch this. This is 2005. There's January, February, March, April, look at that. May, June, July, August, no rain. September, getting a little bluer again. October, bluer. November, bluer. And December, blue again, right? So what we can see there is a pattern, right? So what do we see with that pattern? We see there's some pretty distinct seasonal trends, right? June to August, exactly. So June to August is a long drought, sustained droughts. That's the key. That's the key there, is long sustained droughts. And this is where it gets really interesting. Because it's, so then the other thing we need to think, remember our model, we had rain, precipitation, we had state, so vegetation to savanna. We've got EVI for the state, we've got the rain trim for the rain. Fires, right? Fire is a driving thing. Fire driven by a lot of stuff. Some of them are natural, some of them are fueled through from cattle raising or what have you. So fire is another thing that needs to be assessed over time. So there's looked at the spatial pattern of fire. This image here is 2001 to 2006, aggregate amount of fires to look at the frequency of fires. Where were all the fires? This is Mato Grosso. So what can you see here? You can see that along these big black lines, which are the roads, there's a lot of fires around them, right? In the right-hand side, and then this BR163 has a lot of fires around it, which kind of makes sense, right? If you have access to something, this will start to lead to development of fires. So the key question is to determine human influence on fire presence. So there is a relationship between highway and fire presence. You can look at the kind of before and after, obviously, and relationship of distance to the road and so forth. I did basically a buffer, pretty basic analysis for that one. I didn't have much time. But you can see that there's a relationship in just spatially. But what's even more interesting, though, is to look at the relationship between this stuff, right? The system characterization. And this is where we really get at this idea of how do you measure resilience? What are these turning points that are going to lead to potential state shift? So you can see here, and this is data from the Transect study, right? This is the relationship between EVI and precipitation, which is essentially forest versus rain, right? And so the precipitation is red. I should have been blue, but I just made it as red. And then EVI, which is in blue. And so you can see this is along Site 1, which is quite far. This is a lateral transect, so it's quite far west. Okay, actually Site 1 lateral transect. So I'm just going to go back here. Yeah, so Site 1 in the lateral transect, you see this 1 is way far west. So you'd expect that to be not as influenced because there wasn't as much fire out there. Whereas if you go further to the center, either Site 5 on the lateral or vertical, or 4 on the vertical transect, I would expect to see different characteristics there. This is how you get rough estimation of spatial pattern. So here we can see that at Site 1, we had precipitation go down like it usually does. It goes January, February, March, April. This is January through December on the x-axis, February, March, April, May, June, right? So we know that June, July, August, things get drier, and it happens all the time. You can see that consistently in the data, not just in drought years. And then you can see a bit of dip in EVI, right? So that just dipped down a bit in this is Site 1. Whereas in Site 5 on the lateral trends, that's right in the center where all those fires were, you can see, and this is averaged from 2001 to 2006. So it's just general characteristics. You can see in the center part of Mato Grosso, as this precipitation goes down, it goes way down. So on average, there's far less precipitation further inland, like further towards the center. And then also you can see that this EVI signal goes way down too. So you see a much greater reduction in vegetation in that period. And then you see a big recovery, but it gets hit pretty hard. And that's largely because of the extended and long droughts that it experiences in this area. okay? So the latitudinal transects show you that different kind of how it plays out over space. And the site 5 near the Hawaii showed greater dry season reduction in precipitation and EVI, so it got hit hard in the center part of Mato Grosso. Now, if you look at the system characterization by comparison of a site between 5 years, this is where you look at interannual comparison. This again is site 5. So this is the same site that gets hit really hard during the dry season. We want to see, okay, if this is the area that's going to get hit really hard, what if it gets hit even harder because you have a strong drought year? So the first one up here is 2001, all right? 2001 was kind of a normal year, right? You get a reduction in rain, okay, things go down a bit, and then, you know, it rebounds. But then you look at 2005, and that's the year that you had the drought. And you can see that you see a much more pronounced reduction in EVI. It stays down for a longer period of time, goes down quicker. And you see this drought really bottoms out. So in the bottom one here, you can see in May, like even in April, it starts to go down, but May, it's way down. And then June, it's down. July, it's down. August, it's down. It's like 0 for 3 months. You have no rain, pretty much. This is a big deal in 2005 in the literature, okay? So this drought signal then really has a big impact. This is something we need to be concerned about, because this drought then can really force EVI, the state, to go down and potentially stay down, right? From a rainforest to a savanna. So what else do we need to look at? We need to look at fire frequency, because that's another aspect in our resilience model, right? So this is fire activity over time comparison between, on a season, between 2001, normal season, and 2005, drought season, right? 2005 is a drought. The orange line there is 2001. So you'd see a characteristic pattern, January through December, as you would expect, as the drought comes on in about June, July, August, September, you would expect there to be more fires. Like in BC, you're going to get more fires in the dry season in the summer, to be expected. 2005, where we had the drought year, right? Way up, way to like 2 times the number of fires than you had normally in September during that drought year than you did in 2001. All right, so this is another thing we need to be concerned about. And these are measured, again, from satellites from something called thermal anomalies or hot pixels. So what this is showing you is this is giving us some signals, generally speaking, as to what we need to be worried about in terms of areas potentially shifting, right? So this image here shows the quantification of state change, ecosystem change in Mato Grosso between 2001 and 2005. Classification, how much of there was rainforest in 2001 and how much was savanna. And so what I did here was observed changes, state changes, because there's always going to be change, right? Sometimes there's regrowth, sometimes there's deforestation, whatever. But the thing that was very predominant in Mato Grosso between 2001 and 2006 was the amount of shift from forest to savanna. Way, way, way more observed changes than savanna to forest, like reforestation and savanna to transition. So I had a transition state, forest state, savanna state, and quantified it in that way. So you can see that's a problem, because that's showing that this system at that point in time was moving towards less stability and a state shift. So we go back to this model then. Now this makes a little more sense, I hope, why you draw these funny pictures with arrows and feedbacks and all this kind of stuff, because how do you measure all this stuff? Well, you got to find a way to do it that makes sense. We have seen in this short data that in the period of 2000 to 2006, there had been a state shift from rainforest to savanna. A lot of it has driven from climate drying, from those pronounced droughts, a reduction in evapotranspiration and precipitation evapotranspiration, which would then contribute to that state shift, and then an increased amount of fires, some of which were anthropogenic, some of which were fueled by land use change or climate drying. But this starts to make sense then, I hope. So conclusions in 2008, some indication that large-scale shift was underway. It's difficult to pinpoint specific linkages, and this is the problem with this kind of mesoscale research. It's hard to say it's this policy, because there's multiple things happening at the same time. You got to look at the relative proportion or contribution to different things. Land use policy is a contributing factor for sure, and it's an immediate thing. However, one of the things that was also quite concerning was the fact that that drought, which happens, like it happens cyclically, is linked to, as I researched and met with the folks from their Met service in Brazil, there is a phenomenon in South America similar to the El Nino. So the El Nino is on the Pacific side, which is an east-west dipole change in temperature of the ocean, a shift over large scales from east to west, kind of like a seesaw. A similar thing happens in the southern tropical Atlantic. So the Atlantic Ocean to the east of Brazil there, just in the south, there's a north-south El Nino. It's this dipole, it shifts over years, like on a cycle of years. And when it shifts in one direction, it causes the ocean to warm. So the surface temperature is warmer in the southern tropical sea surface. The sea surface temperature in the southern tropical is warmer at a specific part of that cycle. And that contributes to that drought. That drought, the strength of that drought is synced up to that sea surface temperature anomaly. And there's a lot of literature behind it. So it's a known thing. The other problem is, exactly, well, this is where we're going to get at here, is so knowing that, because you might say, it's all climate change. Well, the modeling and the work that's done on the Earth system, folks, indicate that that sea surface temperature anomaly, the north-south one, gets stronger the greater the amount of greenhouse gas concentration is in the atmosphere. You get a stronger dipole and you get stronger droughts, meaning they're longer and they're more pronounced. So this is a problem then. We got to look at the speed and what can we do about this stuff, right? Well, it's hard to do something. I mean, we could cut out greenhouse gas emissions tomorrow and still have this thing happening for quite some time. And it's not, land use change is not going to stop that, right? That's going to continue based on whatever we do with climate. So there's clearly showing some problems here. And why it's interesting to go through this again, and why I like to bring it up, is because the same darn thing happened in 2019. The same spike in fires occurred, same type of dynamics were at play with even more land use change that occurred, which leads me to think that we're not doing our best at making sure that the Amazon is resilient. We need to think about ways to kind of bolster it, or the predictions of Cox and the other folks that had written about that could be coming true. Now, some other things that came up though in this related work was, and Linda came up with this comment, was that the pronounced drying. You would think that with that level of pronounced drying, all trees would die, right? In some cases, they greened up, they became more green, right? And there was a study that was done on this that said an Amazon green up in response to the drought by a group called a gentleman by the name of Alfredo Huete, who's an expert in remote sensing and forests. And it was quite controversial. How the hell would that happen? And we don't believe your results. But then someone went there, a guy named Dan Nepstad, and did some studies in the forest looking at the hydrology. And he determined that it was the rooting depth. Because the rooting depth of the trees in the Amazon is so deep, they have reserves. They have access to water that they don't normally use. But under that stress, they access that water because of the rooting depth. It's like kind of a safety valve, I guess, or safety hatch. And there was actually pronounced greening in some cases. There's more photosynthesis happening, right? So again, it's like another one of those things thrown. It's like, oh my gosh, okay, maybe that could be something that we can look at as a means of enforcing resilience. So what does it mean for today? And this gets to Jason's point. It appears that the current land use and forestry policy is development oriented today. This is with Bolsonaro. Perhaps a resilience lens could be helpful in order to account for the combined effects of land use and drought. We need to understand the economics drives a lot of this. So the economics drives land use change, soy, cattle, agriculture, what have you. We need to balance the economic imperative, the ecological imperative, and the social imperative clearly is the challenge. So this was an article that was taken from some of the political debate that went on during 2019, when it said Macron must retract insults for Brazil to accept G7 aid to help fight Amazon wildfires, Bolsonaro says. So this is the kind of thing you get into when leaders get up against leaders, and you have like the Macrons of the world who are more progressive, telling the Amazonian leader, President Bolsonaro, to do something. And this is, if you know much about this guy, you know that he probably doesn't take that stuff lying down and tells him to go jump in, you know, jump off the Eiffel Tower or something like that. So this is the kind of, you know, we're dealing with a global commons, but this isn't within Brazil. So this leads into implications for MEA reporting. So how do we deal with this stuff then? We know what the science tells us roughly. What are some things that we can do, and what are some laws that we can enact? Well, one thing is MEAs, and Katya, when she was on, talked about this. They aren't the strongest thing in the world, but at least there's something that can bring these countries together. They're multilateral environmental agreements. They're international agreements that are intended to promote sustainable practices and policies amongst nation states that sign on to them. They're called parties, the states that sign on. There are three frameworks that are particularly relevant to the situation in Amazonia. UNFCCC for climate change, that's the United Nations Framework Convention on Climate Change. UNCBD, United Nations Convention on Biological Diversity. UNCCD, United Nations Convention on Combating Desertification. Those are the Rio conventions, right? They were signed and developed in Rio de Janeiro in like 1992, 93, and then have carried on to this day. And all the COP meetings you hear about, that's the UNFCCC. They each have COP meetings, Conference of the Parties. UNFCCC for climate change stuff, this is your go-to group for policy. International Agreement for Parties includes specific agreements that parties commit to, like, for instance, the Paris Agreement, dealing with commitments to greenhouse gas emissions reductions, adaptation methods, and so forth and so on. The Paris Agreement is the one that's enacted right now. Reporting is a big component of this. So every party needs to then produce a national communication every 2 to 4 years, which is basically their summary of how they're doing along all these different parameters, their carbon footprint and stuff like that. National adaptation plans, so how are they planning to adapt to climate change? Biannual update reports, which again is a periodic report. And NDCs, which are nationally determined contributions. What do they intend to achieve for greenhouse gas reductions? Although the process is thorough and detailed, the problem here, and we'll get to this next week, is there isn't a giant stick for those that don't comply. So if Canada does not meet its greenhouse gas targets for the UNFCCC, there's no one that comes along with a big stick and drags Justin Trudeau out of Parliament, says, Justin, put your hand on the table, and slaps his hand and say, bad boy, you didn't meet your, you didn't meet your target. There's no real, it's more about kind of you let down, and a bit of losing face, I think, is part of it, but there's no like real financial penalties or legal penalties for that matter. They say it's legally binding, but if you don't meet your target, you're not going to like lose, have a tremendous loss. UNCBD, Global Agreement on Conservation and Sustainable Use of Biodiversity, mostly conservation, but incorporates sustainable use. Previous framework was the HE targets. These were 14 targets that were established along different lines to achieve, say, access and benefit sharing, species conservation, invasive species, all these different types of things that need to be taken care of. So that has expired now. 2020 was the expiry of the HE targets, which were developed in HE in Nagoya, actually, in 2011. We're now in the post-2020 framework era, and they're still figuring that out. In fact, we're going to have a guy from the UNCBD in 2 weeks. I think it's 2 weeks, David Ainsworth. We'll talk all about this stuff, what's actually happening, how they work. It's similar to the UNFCCC, various reports that need to be produced. They do a national biodiversity report done by each country, something called an MBSAT, National Biodiversity Action Plan, and other reports. Many challenges with accessing proper data for biodiversity. That's one of the big issues there. And lastly, UNCCD, here's the URL, Global Agreement to Reduce Land Degradation. So several indicators relate to land cover, land quality, soil organic carbon. So a lot of linkages between biodiversity and climate conventions and the climate change conventions. So obviously, if you're dealing with land conservation, you're dealing with preservation of biodiversity, ideally, or certainly on the rainforest side of things, and climate change, reducing greenhouse gas emissions from deforestation. They too have periodic reporting called the ACP, Affected Country Party Report, which is again their kind of periodic benchmark as to how they're doing with reducing land loss. and land degradation neutrality target setting, which is what are their targets to achieve their goal, which is land degradation neutrality by 2030, net zero land degradation. So synergy among them, I'm just going to wrap up here, there's many objectives of the 3 Rio conventions, and it's a lot of overlap between the 3 of them. For example, reducing greenhouse gas emissions from land while promoting is also synchronous or complementary to promoting conservation of biodiversity. Halting land degradation also contributes to conservation of biodiversity and the reduction of greenhouse gas emissions from land degradation, from deforestation, for instance. The challenge is coordinating efforts among different agencies responsible for reporting. And this is the stuff that I work on with my team in different countries. And then enforcing the action. So how do you really motivate or enforce countries to pursue or exceed their targets? A lot of it has to do with, like, you know, bragging rights and just kind of, I don't know, saving face in the eyes of diplomacy. And that's part of what these kind of voluntary international frameworks are like. But as you heard from Katya, it's hard to put a lot of faith in global voluntary frameworks, because, you know, there's no guarantee that they're going to kind of achieve what they're setting out to achieve, and seldom, they don't always, frequently they don't meet those targets. So the SDGs are also important. We've talked about SDGs before as benchmarks that align with these MEAs. The related SDGs that link to those MEAs as well, and that's another kind of task, is the Sustainable Development Goals. So what can we do, though? Back to Jason's question, and in general, now that we're looking at kind of our role as people and scientists and so forth, is land use. So implement sustainable land use practices and economically reward them. That's one way, is to look at ways of getting economic rewards, like Linda brought up agroforestry, which can be very profitable, right? RED, I've brought up here, RED Plus is reduced emissions from ecosystem degradation and deforestation, which is a program in which you can keep forests standing and remunerate those on the ground who are responsible or owning the land by the carbon value that remains in the forest, right? So this is working in Guyana, in a country that we're currently working in, paying people to conserve forests based on the carbon value. Right? That's one tool. Recognize that there are cumulative effects that decrease resilience of Amazonian ecosystems, right? We've seen it's not just one thing. There's a bunch of stuff that's contributing to the degradation of resilience. Therefore, you got to look at these different risks, whether it's a climate risk, building the roads, unsustainable land use, et cetera, et cetera. The other part is to look for details in media reporting. Like, often we get these reports coming up and you're like, okay, well, is it all climate change? Like, climate change we see is a factor here for sure, but it's not the be all and end all. There's a heck of a lot of the problem in the Amazon has to do with land use, going out and chopping down forest and burning it down to do agriculture or raise cattle. I mean, so it's not all climate change there. That's just good old fashioned economic development. And lastly, use capital to mobilize sustainability through design. Example, Canada is sending some water bombers. How about we invest 50 million in sustainable land use and RED activities and joint research in Brazil or Peru or Colombia or whatever, Bolivia. Like, look at these kind of ways of mobilizing capital. We are doing a lot of that right now, or at least we're making announcements about that, but strategically mobilize capital to create some solutions that work for a problem like you've seen tonight, which I think is, you can start to see how this stuff fits together. So strategic analysis can lead to strategic solutions. As an individual, be wise about your purchases. If you know products are coming from unsustainable sources, like fuels that come or produce that comes from deforested Amazonian rainforest, for example, don't buy them. If you're working for a company or in a business network, encourage them to think about implementing an environmental management system or sustainability strategy. It's another practical thing that can be done. You could then build that into a conservation program that aims at issues like deforestation and unsustainable land management, plastics in the ocean, or whatever. So you link your program to some issue, right? So I know companies that focus on reforestation, right? And a good example would be Forest Stewardship Council of Canada is really good at that. Faber-Castell, they're the company that makes pencils and stuff. They do a ton of reforestation. So there's an immense array of solutions out there. We just have to be smart, practical, strategic, and realistic about how we move forward in trying to achieve these targets, and have the analysis, an integrated biospheric analysis to support these decisions. There we go. Questions? That was a mouthful. Any questions? So for those that are, did anyone compare from last year? No, not yet. Well, I have to look at that. That's what I need to look at. I haven't done it personally. I want to do that, but I've just been busy doing things like teaching courses at Royal Roads. Like busy man. I got working in the Caribbean right now. So, so didn't even cover that. So that is on my list, Shona, for sure. I'm keen to do the same analysis. What I'd like to do is extend this analysis and do from 2000 through to 2021 to 20 years. It just takes a while to process the data and stuff like that. It took me a while to do that, like to assemble all the data, do the stats and process. It's laborious. It's faster now, but it still takes time. Is there an indicator to see how resilient an ecosystem is? Well, that's it. We need to come up with the indicators. So what we need to figure out is what are the factors that make any given ecosystem resilient? So what would you think that would be something that would kind of make this system in Amazonia resilient? What would be something that, I have an idea. I'm just going to see what your thoughts are. What would be one factor, I did mention it already, that would potentially contribute, from what we know, from what we've seen of how these things work, would contribute to the resilience? Something we can measure beforehand and say, oh, well, this is pretty high here. So if there is if there's a factor that's, rain is one, but I'm talking about like an indicator, close. You're getting it close with groundwater. What's related to groundwater? What do you need? What does the rainforest need to get to groundwater? Close, come on. How does the water get to the tree? There we go, Shona for the win. Yeah, roots. To me, that would be one of the main ones. I would measure root density and root depth. Find a way to measure that for forests in the Amazonia. And from what I'm seeing so far, that's going to be something that is going to, more roots and deeper roots will be more resilient, I would say, to whatever the hydrological conditions are. Whatever drought's thrown at you, a tree with greater rooting density and rooting depth is going to fare better than one with less. And there would be a critical threshold, I would think, right? So that would be one indicator I'd look at based on what we're seeing and what the work that has been done on above ground, looking at changes in greenness, change in precipitation, and then measuring of rooting depth, which is what Dan Nepstad did. So roots are important, which you wouldn't think about it. I mean, you would if you were a forest person, but it's not the first thing that jumps out at you. Would that include root health? Yeah, I don't know. I'm not, I presume root health would be on there as well as depth. Yeah, it would be root quality. You'd have to come up with something like that. I would think you'd want to make sure that they're able to uptake water well, all that kind of stuff. But I would say root vitality and root depth and density would be some aggregate indicator that what I would throw in the mix there. But you see that that's another thing we would throw into it. We'd throw that into our model and say, well, hey, guess what? It may be a state shift, but if those trees have like super strong roots or super deep roots, it's going to hang on there for a while. And you can have like a drought for 5 months. They should be okay. It's a non-intuitive thing, but certainly something we need to build into our heuristic model. So that model is a heuristic. Strong roots, absolutely. Strong roots, strong tree. So does that kind of, like for those taking the course, does that kind of help you see how you can look at some of these problems? Like a fishery, for instance. you could do this same analysis for a fishery, like the Cook Inlet fishery. Say, okay, well, what are the different states here? Well, we've got, it's not a forest and a savanna. We might be most concerned with a vibrant fishery and a dead fishery, right? And what are the things that sustain a vibrant fishery, right? Capability to spawn, like enough spawning habitat. You're going to have controlled fishing, so that the rates of extraction don't exceed the amount of reproduction that occurs. You'd also want to think about the biophysical environment. Maybe there's some factors like climate change, which is contributing. Like sea surface temperature change above a certain threshold may lead to profound impacts on reproduction, spawning habitat, right? So those are the things you got to like identify and map out when you're looking at analyzing these problems to come up with some sort of functional framework for the model that you're looking at, the system that you're looking at. And you can add in these driving factors like extraction of fish, commercial extraction, sport fishing extraction. You can even start with that and then actually process model it. Like you then actually use Stella or something like that to put some rates to things and so forth to see how the dynamics of the model work, like a simulation. All right, but very, very powerful approach to getting a lot of different people to look at something and understand how it works, and hopefully come to some conclusions as to what the best way forward is from a policy standpoint, from like a co-management standpoint, or a regulatory standpoint. What are the rules? How are we going to govern the commons, right? So I'm a big fan of that, of using this kind of process model, process diagram, heuristic models to show the system so people can see that, you know, this is how climate change is affecting this, or how we think it's affecting this. This is how like resource use is affecting this. This is how, say, I don't know, hydro expansion is affecting this through siltation, affecting habitat for a fishery, right? And that really gets people to see all the stuff on the same page at the same time. Any other questions? It would be faster to do the analysis now for me because I was learning it at the time too. I didn't know what I was doing when I started. And then by the time I finished that, you know, 2-3 years in, I was like, it was much quicker. Now I'll be like, you know. Good. All right. Well, good. Yeah. I mean, with climate, you look at the speed of variables too. Climate is a slow variable, tends to be, whereas some of these things are faster. We didn't really talk about that speed. Land use change is a fast variable. You put in a policy to open up development, boom, forest gets cut down. A place like Brazil or other parts of South America. Climate, that's a decadal or multi-decadal phenomenon. You're going to get these acute things that happen, like these droughts that seem to be linked to it, but it's not as like quick as these other things. So you look at the speed of variables as well, which is another important part of this whole process. Quick variables and slow variables. All right, well, thank you for coming out. It's been recorded, so those that couldn't make it, you are welcome to take a look on your spare time or pass it on. It will be on YouTube probably tomorrow. And hopefully this has been somewhat interesting. And also I like doing this presentation because I put data to a model, especially geospatial data. So you can literally see over a map how these things, where you get the data from and how it plays out when you're doing temporal analysis, which is not often the case.